So this is linear algebra, lecture 2. And let me review what we did on Monday. We were looking at solutions of one linear equation, and that brought us to the vector space Rn, which is the set of all n-dimensional column vectors. So an element x in Rn is this column of real numbers, x1, x2, down to x of n. That's a column vector. There are n coordinates. So xi is the ith coordinate of x. So there are nice pictures we can draw in 2 and 3 dimensions. In R2, we can think of a vector as having coordinates x and y, or x1 and x2. If you take the vector x equal, for example, 2, 3, here's the point in the plane with coordinates 2, 3. You can think of a vector like that if you wish. And you dealt with vectors in Calc 3. If you took Calc 3. In R3, harder to draw, sort of like 3-dimensional space, and you can think of a vector as going somewhere in R3, but once you get to dimension 4 or greater, can't draw a picture. And there is simple vector algebra. We have the operations of vector addition. If we have x is the vector x1, x2 down to xn, and y is the vector y1, y2 down to yn, then you get the vector x plus y just by adding coordinates. And we also have the operation of scalar multiplication, where a scalar is just the name for a number in linear algebra. So if you have the vector x and you multiply it by c, so this is c times this column vector. You multiply each coordinate by c. So for example, in R4, if x is the vector 2, 0, minus 3, 7, y is the vector 8, 1, minus 1, minus 9, and c is, let's say, the scalar 7, then x plus y, you add these two vectors. You're adding 2, 0, minus 3, 7, and 8, 1, minus 1, minus 9, and you get 10, 1, minus 4, minus 2. And if you take the vector x and multiply it by 7, that's 7 times the vector 2, 0, minus 3, 7. You multiply each coordinate by 7, you get 14, 0, minus 21, 49. So that's vector addition and scalar multiplication in Rn, which is certainly not the only vector space, but the most important vector space in linear algebra.
Professor?
Yes.
I have a question. The last 2 rows, can you explain that one more time, please?
The last, this and this?
Yes.
So here's a vector. The coordinates, it's a vector in R4. So it's a column of 4 numbers. This particular vector happens to be 2, 0, minus 3, 7. The vector y has coordinates 8, 1, minus 1, minus 9. and I want to add the two vectors. And the way you add vectors is add coordinates. So for x, the first coordinate is 2. For y, the first coordinate is 8. When you add x plus y, the first coordinate is 2 plus 8, which is 10. And so on.
Okay.
Here, if I have the vector x, 2, 0, minus 3, 7, and I'm multiplying it by the scalar 7, I multiply each coordinate by 7. So here, the first coordinate is 2, so 7 times that vector. The first coordinate is 7 times 2, which is 14. And so on.
And where it says 7x equals, is that a 7 after the equal sign?
Yeah, this is 7x. This 7 is this 7, and x is this vector. This is the vector x.
Okay. I understand you said to multiply 7 by 2, that gave you 14. And what does the 7 after the equal do?
Well, it doesn't do it. It's you're saying, like, what does the number 7 do? 7 is 7. 7 is a number. X is a vector. I'm giving an example of multiplying a vector by a scalar. This is just an example of scalar multiplication.
Thank you.
Right? If you have any scalar and any vector, you can multiply them. If you have two vectors, there's no way to multiply them. That makes any sense for us. But we can multiply a scalar times a vector. Right? Now, for us, vectors arose when we looked at linear equations. So a linear equation, one linear equation in n variables, it's an equation that looks like a1x1 plus a2x2 plus anxn equals b. This is one linear equation. The variables are x1, x2 up to xn. And we're interested in solutions of that equation. Again, what we use as our symbols for the variables is not important. Here I'm using x1 up to xn. If n equals 2, if we like, we can use x and y as the variables. If n equals 3, we could use x, y, and z as the variables. It's completely up to us. So I could look at the equation 4x1 plus 7, sorry, 4x1 plus 7x2 equal 5. Or I could write it, look at the equation 4x plus 7y equals 5. It's the same equation. I'm just using different letters for the variables. I could use 4r plus 7s equals 5. Again, the letters I choose for the variables are not important. And so, for example, all right, so here we have a linear equation, and we say that a solution of the equation is a vector x with coordinates x1 up to xn in Rn that satisfies the equation. And the solution space is the set of all vectors that satisfy the equation.
I'm sorry, the symbol right before RN, can you just clarify what that means?
What's the, oh, this?
Yes,
In. So
thank you.
Rn is the set of all vectors, and this is an element in that set. So this is this is that's a form of the Greek letter epsilon.
Thank you.
So let me just, to make things as easy as possible, let me pick an equation from the notes. Or actually, I'll pick one of the homework problems.
I have a question.
Yeah,
On the last page that you just turned over, the last part where it says 4n plus 7s equals 5, you were just showing us that we could just use different
well,
variables.
this is 4r plus 7s, 4x plus 7y, 4x1 plus 7x2. It doesn't matter what letters you use. They're just letters, they're names for the variables,
Okay.
right? Okay. So suppose I want to solve the equation x plus 3y equals 1. I want to find the solution space. So if I have any solution, x is going to be 1 minus 3y. So if I write the solution as the color vector xy, x is 1 minus 3y, y. So all vectors of this form are solutions of this equation. I can write this as follows. Let me just, you never would do this except when you're learning a little bit. You can think of y as 0 plus y. This is the sum of the vectors 1, 0 plus minus 3y, y. And this is the vector 1, 0 plus y times the vector minus 3, 1. So if you just work out using the most elementary, the little bit of vector algebra that we did, you take the vector minus 3, 1. If you scale or multiply it by y, that's minus 3y over y. You add 1, 0 to that, you get 1 minus 3y over y. That's what any solution of this equation has to look like. So the solution space is the set of all vectors of the form 1, 0 plus y times minus 3, 1, where y can be in any number in the set of real numbers. Right? So this is how you write mathematics. This is set theoretic notation. Right? This is a set. Y is any number in the set of real numbers. Right? So this is the solution space of this equation. This is a set of vectors, and a vector is the solution of the equation if and only if it lies in this space. Now, so any questions about that as a start? This is like an equation in two variables is going to be the simplest equations we study, and we're not going to study them that much because they're so simple.
I have a question.
Yeah.
In the solution space where you put parentheses 1 and 0 plus y and negative 3 and 1, that's just showing this from the start and the end of the solution space.
So this is a vector. This is one vector.
Okay.
And this is a vector in the solution space. Right. So if you compute this vector, this is what it is. It's 1 minus 3y is the first coordinate, y is the second coordinate. If you plug that into this equation, you get a solution. For example, suppose I take y equal to 8. Then 1, 0 plus 8 times minus 3, 1. That's 1, 0 plus minus 24, 8. That's minus 23, 8. So this vector is equal to this. And if I take that vector and plug it into the equation, so in this case, x is minus 23. This is what we get. X is minus 23, y is equal to 8. So x plus 3y is minus 23 plus 3 times 8. That's minus 3 plus 24. That's equal to 1. So it does satisfy this equation. And every vector, no matter what number I pick for y, I get a vector that solves the equation. And every solution of the equation is of this form. Right?
And where did you get negative 24 from?
8 times minus 3.
Okay, got it.
Now, when I solved this equation, I decided, it was a little bit simpler, to solve for x in terms of y. If I solve this equation for x, I get x is 1 minus 3y. But I could have chosen to solve for y in terms of x. And we get the same solution space, but it's written in a different form. So if I have x plus 3y equals 1, so 3y is 1 minus x. So y is 1 minus x over 3, or 1/3 minus 1/3 x. So if xy is a solution, then for any x, y has to be 1/3 minus 1/3 x. Right? Right? Y, given x, y has to be this. And if I want, I can write this as the vector 0, 1/3 plus the vector x minus 1/3 x. And I can factor out the scalar x. This is 0, 1/3 plus x times 1 minus 1/3. So another way to write the solution space of this equation is the set of all vectors 0, 1/3 plus x times 1 minus 1/3 for any real number x.
Professor,
Yeah,
why do we switch from y equals to 1 minus x over 3 to 1/3 minus 1/3 x? Like on the top. Couldn't you just leave it as a 1 minus x over 3? Y equals to? Yeah, right there.
y equals 1 minus x over 3.
Yeah, couldn't you just leave it as that and then solve it?
Well, that is the solution. I mean, this is just another way of writing it.
Yeah, like
And
simplified
I
it.
chose to do it like this because I wanted my solution space to be of the form a fixed vector plus a scalar multiple of another vector. If I left it in this form, I wouldn't get this. I mean, so easily. I mean, this is what it is. I could get it, but I have to go through this kind of elementary arithmetic.
Okay, so whenever we get that form, we should simplify it to that to make it easier for us.
Whatever works. I mean, it's not like there's a general rule about this. You solve a lot of problems and you develop some technique, some technical skill, but you want to get the solution space to look something like this. A fixed
Okay.
vector plus scalar multiples of some other fixed vectors.
All right.
Okay. Let's look at another example. Suppose I take the equation x plus 3y minus 7z equals 1. So this is solutions in R3. There are 3 variables. So the solution space is contained in R3. This means contained in, or subset of, same thing. So I want to find all vectors x, y, z in R3 it solved the equation. So if you have a solution of the equation, if x plus 3y minus 7z equal 1, then certainly x is going to be equal to 1 minus 3y plus 7z. So if I choose any values at all for y and z, I have no restriction on what I can pick. But if I choose, once I pick y and z, x has to be equal to this. Right? So if x is a solution, if x, y, z is a solution, x has to equal this. And if x is equal to this is a solution. And if I want, I can write this as the following. Not just, I'm going to do something which, again, you would never do, except maybe when you're learning how to do this little bit. This is y, and this is z. This is sort of like 0 plus 0, 0 plus 0 plus. I'm just trying to line this up so in my imagination, this vector, I have the scalars, the y's, and the z's in sort of columns. So I can write this as a sum of the following three vectors: 1, 0, 0, plus minus 3y, y, 0, plus 7z, 0, z. And so that's 1, 0, 0. That's one solution. That's a particular solution of the equation. Plus, I can factor the scalar y out of this. This is y times the vector minus 3, 1, 0. And I can factor the scalar z from this vector. This is z times the vector 7, 0, 1. So every solution, here's my linear equation. Every solution of that equation is this vector plus a scalar multiple of the second vector and a scalar multiple of this third vector. So the solution space, I can say S, or say the solution space, is the set of all vectors of this form where y and z can be any scalars, any real numbers. That's what the solution space looks like. And when you do your homework and when you take exams, you have to be able to write the solution space of an equation in this form.
I have a question.
Yeah.
I don't really understand the last two columns that you wrote.
This column and this column?
The column on top and that column as well.
Okay, so here we have the equation. X plus 3y minus 7z equal 1. If you have a solution, then, that is, if x plus 3y minus 7z equals 1, if I solve for x, x has to be 1 minus 3y plus 7z. So if you write your vector x, y, z, y is y, z is z, but x must be 1 minus 3y plus 7z. This is what every solution is of this form. And then I'm simply decomposing this vector into a sum of three vectors, this plus this plus this. And why is that true? Because if you add these three vectors, and you add vectors by adding coordinates, the first coordinate when you add these three vectors is 1 minus 3y plus 7z, exactly this. The second coordinate when you add these three vectors is 0 plus y plus 0, that's this. The third coordinate when you add these three vectors is 0 plus 0 plus z, that's this. So the solution, and then this vector is y. I can take the scalar y outside. This is y times the vector minus 3, 1, 0. This is like 1 times y, 0 times y. This is y times the vector minus 3, 1, 0. Right? That's where this comes from.
Okay, I understand. And then the last one on the bottom,
Yeah. So this is the solution space. Every vector that's this particular vector, 1, 0, 0, plus y times this plus z times this. For every choice of y and z, you get a solution of the equation. And every solution of the equation is of this form.
where did you get the middle part where it says y parentheses negative 3, 1, and 0?
It's right here. This is minus 3y, y, 0. This is y times minus 3, 1, 0. If I multiply this vector by the scalar, this is what I get.
Okay, no problem. And then it says equal to y, z, and
No,
then
it's
all.
not equal. This is a colon.
Oh, that's a colon.
Yes. So
Explain the ending where you after the colon.
So this is a set. So we put a set inside curly brackets. And it's the set of all vectors that's of this form that satisfy this condition. That's what this double colon means, where y and z are real numbers in the set of real numbers.
Okay, thank you. Will these notes be uploaded to a playlist for us?
So it's all in the book, right? The book is on Blackboard, right? Everything is from the book that I posted on Blackboard, and yeah, that's where it comes from.
So I see that it's recording. So where does the recording go?
So I'm having the recording will be posted on YouTube, but I have for some reason I have some problems getting on YouTube at the moment. So as soon as I can deal with those problems, I'll send out an email, and you'll be able to see the videos of the lectures on YouTube.
Okay, thank you.
Okay. So let's just continue. Again, this is all review of what I did on Monday. So let W be a subset of the vector space Rn. So W is what is called a subspace of Rn if it satisfies the following three conditions. First, 0 is in W, and 0 is the zero vector. The zero vector is the n-dimensional vector whose coordinates are all 0. So a subspace must contain the zero vector. Second, W has to be closed under vector addition. This means that if x and y are two vectors in W, then x plus y is in W. That's what closed under vector addition means. And third, W must be closed under scalar multiplication. This means that if x is a vector in W and c is any scalar, any real number, then c times x is in W. So that's what a subspace is. And the important theorem says that so again, in the notes, this is theorem 12 on page 19 of the textbook notes. It says the following. The set W of solutions of the homogeneous linear equation is a vector subspace, is a subspace. Suppose the equation is a1x1 plus a2x2 plus anxn. This is an equation in n variables, and homogeneous means the right-hand side is 0. So the solutions are going to be vectors that have n coordinates, n-dimensional. So the solution space of this homogeneous linear equation is a subspace of Rn. So that's what we have to prove, right? This is a 300-level math class. It includes proofs. So why is this statement true? Well, first of all, we have to show that the 0 vector is in the subspace, is in the solution space. So if I take a1 times 0 plus a2 times 0, by that every variable would be 0, I'm just adding a lot of zeros, I get 0. So this means that the 0 vector is in W. So the first condition of a subspace is satisfied. Suppose X, the vector X is in W, and the vector Y is in W. So what does that mean? It means this is a solution of the equation. a1x1 plus a2x2 up to anxn is 0. And this is a solution of the equation. a1y1 plus a2y2 plus anyn is 0. Add these two equations. This plus this is a1 times x1 plus y1. Add these two, you get a2 times x2 plus y2. And all the way along, when you add the last two terms, you get an times xn plus yn is 0. So I have a new solution of this equation, and these are the coordinates. So x1 plus y1, x2 plus y2, down to xn plus yn. This is in W, but this is exactly the sum of the vectors x and y. So if x is in W and y is in W, then x plus y is in W. So W is closed under vector addition. And if I look at the vector c times x, that's the vector cx1, cx2 down to cxn. That's the vector I get when I multiply every coordinate by c. Is this the solution of the equation? Well, a1 times cx1 plus a2 times cx2 up to an times cxn. I can factor a c out from each of these terms. That's c times a1x1 plus a2x2 plus anxn. But what's inside the square brackets is 0. This is c times 0, and the product of two numbers, and one of them is 0, is always 0. So this is a solution. This is in W. So that's the end of the proof. I proved that if you have a homogeneous linear equation, the solution space is a subspace.
I didn't really understand, Professor.
Well, let me give an example. Suppose I take an equation like 4x plus 7y equals 0. Okay? That's an equation. Homogeneous. This is homogeneous. How many variables in this equation?
2.
Homogeneous, 2 variables. So what's one solution? You could have
I mean, both variables are 0, is equal to 0.
sorry?
If x and y is 0, then the solution is 0 as well.
Oh, okay. So 4 times 0 plus 7 times 0 is 0 plus 0 is 0. So suppose I let W be the solution space, which is in R2. So this says that the vector 0, 0 is in W, the 0 vector. Because the x equals 0, y equals 0 gives a solution. Let's see, what's another solution? I could take suppose I take the vector xy equal to 14 minus 24. So 4 times 14 plus 7 times minus 24. 4 times 14 is, oops, let's see, let me do my arithmetic better. Make this minus 8. So 4 times 14 plus 7 times minus 8. What is that? 4 times 14 is 56. 7 times minus 8 is minus 56, so that's 0. So the vector 14 minus 8 is in W. What's another solution? I could take, I don't know, I could take x to be equal to 1 and y to be equal to minus 4/7. So 4 times 1 plus 7 times minus 4/7 is 4 minus 4 is 0. So this is also a vector in W. Suppose I add these vectors. 14 minus 8 plus 1 minus 4/7. See, what do I get when I add them? I get 15. 14 plus 1 is 15. Minus 8 minus 4/7. Well, if you can add fractions, I think this is minus 60/7. That fraction. So 4 times 15 plus 7 times minus 60/7 is 60 minus 60 is 0. So this is also in W. So this is just an example. This vector is a solution. This vector is a solution. And when I add them, I get another solution. Right? That's all we're saying, that if you have a homogeneous equation, the sum of 2 solutions is a solution. Right? Now, it may be that the way we're solving equations is more abstract than what you're used to seeing. Certainly in high school, and more abstract than perhaps in calculus. But that's because you're getting into more advanced mathematics, and it's not as easy as calculus, perhaps. Some sense it's easier, but there are more, if you like, abstract concepts that you have to learn. That's what the subject is about. Let's go back to talking a little bit more about subspaces. This is actually in my notes, page 9. But this would be page 10. So we know we have, if x and y are vectors in Rn, then we know that we can add them. And we can also, if c is a scalar, if c is a real number, c times x is in Rn, right? So in Rn, we have vector addition, a binary operation, and scalar multiplication. So suppose I take k vectors in Rn and k scalars. So I can take the vector x1 and multiply it by the scalar c1. I can take the vector x2 and multiply it by the scalar c2. If I have a vector x3, I would multiply it by the scalar c3 and so forth, all the way up to the vector xk multiplied by the scalar ck. So I can take each of these vectors and multiply them by scalars. And then I can take these first two vectors and add them. And then I can add this vector to this. And I can just keep adding all these vectors. And this expression is what is called a linear combination. A linear combination of the vectors x1 up to xk. So for example, in R2, if I had x1 equal the vector 2, 3, x2 the vector 0, -4, x3 the vector -1, 1, and c1 equal 5, c2 equal -8, c3 equals 7. What is the linear combination c1 x1 plus c2 x2 plus c3 x3? So this is really just elementary arithmetic with vectors. You have to learn how to do this quickly and correctly, and just do a lot of examples and you'll acquire the technique. So what is c1 x1? c1 is 5 and x1 is the vector 2, 3. What is c2? It's -8 times the vector x2. c3 x3 is 7 times the vector -1, 1. Right, I'm computing this linear combination. 5x1 -8x2, 7x3. What is 5 times this vector? 10, 15. What is -8 times this vector? 0 minus times minus is plus is 32. What is 7 times this vector? -7, 7. You add vectors by adding coordinates. The first coordinate, 10 plus 0 minus 7 is 3. Second coordinate, 15 plus 32 is 47, plus 7 is 54. So this linear combination of these three vectors with these three scalars gives the vector 354. Right? So let's pause for a moment and just yourself with a paper and pencil, write down these three vectors, these three scalars, compute this linear combination, and make sure this is what you get. And after you've done that, compute a different linear combination of these three vectors Suppose I take minus 2x1 minus 5x2 plus 4x3, calculate that, and tell me what you get. Let's see. A couple people got minus 8, 18. Well, the only way I know to do it is to do it. So let's see. Minus 2 times 2, 3. Minus 5 times 0 minus 4. Plus 4 times minus 1, 1. So minus 2 times 2, 3 is minus 4 minus 6. Minus 5 times 0 minus 4 is 0, 20. And 4 times minus 1, 1 is minus 4, 4. So if I get that, add that up, I get minus 4 plus 4 is minus 8. Minus 16 plus 20 is 14, plus 4 is 18. Excellent. So if that's what you got, good for you. That's what it is.
Wait, Professor, can I see that one more time?
Sure.
So I got right up to the second last one. It ends in -1 and 1. Can
Yeah.
you explain the last part?
Well, 4 times that vector, minus 1, 1, is the vector minus 4, 4. Right? And this is the vector scalar multiplied by 4. You multiply every coordinate by 4.
Okay, and then in the middle, does that say 0W?
So this is the vector 0 minus 4. It's exactly this vector we've been working with. 0 minus 4 is the second vector. And the first vector is 2, 3.
But the one on the right-hand side, all the way at the end, I see in the middle 0W.
No, this is minus 5 times 0 minus 4. If you multiply this vector by minus 5 times 0 is 0. Minus 5 times minus 4 is plus 20.
Okay, that's 20. Okay.
Right? But it's just 5 times 4. So there's no reason a letter would suddenly pop up there out of nowhere.
And okay, so then it's -4 because -2 and 2 is 4, and then okay, I got it. I understand.
Okay, good. And linear combinations are important everywhere in linear algebra. And on page 17 in the text, there's lemma 1.2. We have the vector space Rn and a subset W of Rn is a subspace if and only if. So this double-headed arrow means if and only if. So a subset W of Rn is a subspace if and only if W is non-empty and closed under the operation of taking linear combinations. And that means that every linear combination of vectors in W belongs to W. And from that, we get theorem 1.1, which says that V be equal to the vector space Rn, and S a non-empty, something is in there, subset of V. If you take the set of all linear combinations of vectors in S, this is a subspace of Rn, and this is the smallest subspace of Rn that contains S. It's called the subspace generated by S. So all I'm saying here, and again, you have to begin to think a little bit abstractly about vector spaces and their subspaces. Sets a subspace if it's non-empty and closed under taking linear combinations. And if you take any set, which is certainly not necessarily a subspace, but if you look at all the linear combinations of vectors in S, that forms a subspace, and it's the smallest subspace that contains S. So these are sort of general facts, if you like, about subspaces. And the theorem says that if you have a homogeneous linear equation, the set of solutions is a subspace. Remember, a homogeneous linear equation in n variables looks like a1, x1, a2, x2, a3, x3, up to an, xn equals 0. This is homogeneous. But suppose the right-hand side is not 0, it's some number b different from 0. So then this equation is called inhomogeneous. And what can we say about the solutions of an inhomogeneous equation? That's the next thing we have to look at. And let's take a look. So we have to define what happens if you take a subspace and you translate it. By the way, let me just show you a picture of a subspace. Suppose we take the vector space to be R2, and we take the subspace W to be, let's say I take this line, this is the line through the origin, y equals 2x. So a vector, a point on this line, if the coordinates are x, comma 2x, or x times the vector 1, 2. So if I let W be the set of all scalar multiples of the vector 1, 2, that's just this line. This line is W. So here's a nice picture of, here's your vector space R2. I take the line y equal 2x, all the points on that line, write it as a vector, xy, but y is 2x, so it's x, 2x, or x times the vector 1, 2. That's a subspace. This is a subspace whose y-intercept is 0, y equal 2x. Suppose I take the line y equals 2x minus 3. That's the line whose y-intercept is -3 and has slope 2. So this is the line y equals 2x minus 3. It has slope 2. These two lines are parallel, but it doesn't go through the origin. This parallel line is not a vector subspace, but I will explain right now why this parallel line is what is called an affine subspace. The way you get an affine subspace is you take a subspace, in this case a line through the origin, and every line parallel to that, that means it's y equals 2x plus b, where b is the y-intercept. Every line parallel to this is what is called an affine subspace. So you have this whole family of affine subspaces parallel to this vector subspace. Right? And one way to describe this, let's see. So what does a vector on this line look like? For any x, y is 2x minus 3. This is like the sum of the vectors 0 minus 3 plus x 2x, or 0 minus 3 plus x times the vector 1, 2. Now, x times the vector 1, 2 is a point on the subspace through the origin. But then to every such point, I'm adding this fixed vector 0 minus 3. What does 0 minus 3 look like? 0 minus 3 is this vector. It's pointing down 3 units. And it's like if I take this line and I move it down 3 units, I get from the pencil color line, the gray line, to the red line. Okay? So this is a translation. We call this a translation, which just means a movement of the gray line to the red line by pushing it down 3 units like this. Right? So if you have this picture in your mind, that's a very good way to think of what I'm about to define as an affine subspace.
I have a question.
Yes.
How did you get y equals 2y? How did you get those coordinates?
Well, I start with the line y equals 2x. Right? That's where I'm starting with. I just picked that line.
Okay.
My choice. So if y is 2x, if you write it xy, y is 2x. So this is a point on this line, a vector on this line, written as a column vector is x, 2x, because the second coordinate y is 2x. And this is the same as x times the vector 1, 2. Then I pick another line parallel to this. Two lines are parallel. They have the same slope. Y equals mx plus b. M is the slope. This line is slope 2. This line is slope 2. In high school, they taught you this is y-intercept 0. This is y-intercept minus 3. But they're parallel lines. In this case, given x, y is 2x minus 3. And I can write this, I can decompose this vector as 0 minus 3 plus x times 1, 2. Right? This is just elementary vector algebra. I'm doing this.
Okay.
All right. And I think of this as a translation of this gray line. I'm moving the gray line to get the red line. So in general, if we have x and w subsets of Rn, I define the sum set x plus w to be all vectors little x plus little w, where x is any vector in x and w is any vector in w. But if more to the point, if I take a vector v in Rn and a subset w or a subspace w contained in Rn, then V plus W. V is a fixed vector. This is, I add V to every vector in W. This is the important definition. This is, I'm translating, this is the definition of what a translation is in a vector space. This is translation of the subspace W by V. And if you take V as a vector if you take V as a W as a subspace, and you translate it by a vector V, that is what is called an affine subspace. So an affine subspace is the translation of a subspace by a vector V. And so this is an affine subspace. This line, it's the vector 0 minus 3 plus W, where W is this subspace, this line, y equals 2x. So the only new thing we're doing today, everything I've done so far is just a review of what we did on Monday. The only new thing is I just defined an affine subspace, and I'm going to show we get the following theorem. So this is in the text. Theorem 1.3. This is on page 23. So what you're supposed to be studying really is the text, right? The text is the course. And the lectures are lectures on the text, but the text is what's important. That's what you have to know. So the theorem says the set L of the non-zero linear equation a1x1 plus a2x2 plus an(xn) equals b. So this is, b could be 0, that's the homogeneous equation, but b can also be non-zero, which is the inhomogeneous equation. In all solutions, in all cases, the set of solutions, set L of solutions of the non-zero linear equation. Non-zero means at least one of these coefficients, at least one of the a's is non-zero, is an affine subspace of Rn. Okay. So if you have the homogeneous equation, the solution space is a subspace. But if it's inhomogeneous, the solution space is an affine subspace. So proof. Every non-zero equation has at least one solution. So we proved that. That was that first lemma on Monday. Suppose V with coordinates v1, v2 down to v sub n in Rn is a solution of, let me call that equation star. So this means that a1 v1 plus a2 v2 plus an vn equals b. When you plug these numbers into the equation, you get a solution. That W be the subspace of solutions of the homogeneous equation.
So, Professor, homogeneous, it has to equal to 0,
Correct.
and non-homogeneous, it has to equal to a number,
Yes.
either a number or a letter.
Inhomogeneous, the right-hand side is not 0. Homogeneous, the right-hand side is 0.
Okay. Can we do an example of inhomogeneous?
Oh, well, we've seen lots of examples. I mean, here's an example. 2x plus 3y equals 7. So one solution is xy equals 2, 1. Because 2 times 2 plus 3 times 1 equals 7. So that's an inhomogeneous equation, and there's a solution. All right, this is exactly, yeah, this, right, this is, pre-calculus. Only now we have possibly more variables, so it's more complicated, but that's really all it is. So that W be the subspace of solutions of the homogeneous equation. And that W with x1 down to xn, this is a vector in W. So this is 0. Now, I have this equation, this equals B. I have this equation, this equals 0. Suppose I add these two equations. So I get A1, B1 plus X1, plus A2, B2 plus X2, plus AN, BN plus XN equals 0. Sorry, equals B plus 0 equals B. So a solution of the homogeneous equation, B plus X, that's the vector with coordinates B1 plus X1 down to Bn plus Xn. This is in L. L was the set of solutions of the inhomogeneous equation. If V is a particular solution of the homogeneous equation, and X is any, or W is any solution of the inhomogeneous equation, of the homogeneous equation, then V plus W is in L. So if I take this particular solution of the inhomogeneous equation, and I add to it any solution of the homogeneous equation, I get a solution of the inhomogeneous equation. So V plus W is contained in L. Okay. On the other hand, suppose V prime with coordinates V1 prime down to Vn prime is also in L. So this means that A1 V1 prime plus A2 V2 prime plus AN Vn prime equals B. We also had V was in L. V had coordinates V1 up to Vn. So A1 V1 plus A2 V2 up to AN Vn equals B. And now I take these two equations and I subtract them. And I subtract this minus this, that's A1 V1 prime minus V1. This minus this is A2 V2 prime minus V1 and so forth. When I get to the last term, it's AN Vn prime minus Vn equals this minus this, B minus B, which is 0. That means the vector V prime minus V, and these are the coordinates, V1 prime minus V1 down to Vn prime minus Vn. This is a solution of the homogeneous equation. So v prime minus v is some vector w in the subspace of homogeneous equations. So v prime is equal to v plus w, which is in v plus the translate of this subspace. For every v prime is an arbitrary vector in L. So that means L is contained in v plus w. But I had proved a moment ago that v plus w is contained in L. So every vector in L is in v plus w, every vector in v plus w is in L. That means L equals v plus w. And this is what an affine subspace is. This is the definition of an affine subspace. So the solution of an inhomogeneous equation is some affine subspace, always. And let me do a couple of examples to try and make this a little bit more concrete. Again, this is all in the text in notes that are legible and relatively cleanly written and so on. So let me do a problem. Suppose we have the equation. Here's the inhomogeneous equation. Three x minus 2y minus z equals 5. Let's consider the homogeneous equation. That's setting the right-hand side equal to 0. The homogeneous equation associated with this is 3x minus 2y minus z equals 0. So suppose we let w be the subspace of solutions of the homogeneous equation. So if x, y, z is a solution of this equation, z is going to be equal to 3x minus 2y. So if x, y, z is a vector in W, or x, y, z is in W, if and only if, for any x and y, z is 3x minus 2y, which is the same as x0, 3x plus 0y minus 2y, which is the same as x times the vector 1, 0, 3, plus y times the vector 0, 1, minus 2. So W is the subspace that consists of all linear combinations so this is a subspace that's the solution of the homogeneous equation.
Professor,
Yes.
can you explain the last part where it has two parentheses? It's x 1, 0, 3, and then plus y 0, 1, and then I believe that's negative.
So this says that if x, y, z is in W, is a solution of the homogeneous equation, then that vector x, y, z is in fact a linear combination of this vector and this vector. Because z has to be equal to 3x minus 2y. So x, y, z is x, y, 3x minus 2y. And if I separate the x and the y parts of this vector into two vectors, this is the sum of these two vectors, which is this plus this. For any numbers x and y, any scalars x and y. So the solution space W of the homogeneous equation is a set of linear combinations of these two vectors. That's what this is. For any x and y, you get a solution of the homogeneous equation, and every solution of the homogeneous equation is of this form.
how did you get 1, 0, 3, and then the other parentheses 0, 1, negative
Here, do
2?
you see how I got x0, 3x?
Yes.
So factor the x out of that. If I take x times this vector, this is x0, 3x. This vector is this vector. They're exactly the same thing. I just factored out the x. X times this is the vector x0, 3x. x0, 3x. This vector is this vector.
And the next column?
Same thing. This vector is this vector.
So that's negative 14, and then you went to
No, there's
negative
not
2.
negative 14. Where's
And-
negative 14?
What is that negative? It looks like a 1 and a 4.
This is 0.
That's negative 2y.
This is negative 2y, which is the same as y times negative 2.
Oh, okay. All right. Thank you.
Okay. Now let's look at the inhomogeneous equation. The inhomogeneous equation, 3x minus 2y minus z equals 5. So if x, y, z solves this equation, if I solve for z, z is equal to minus 5 plus 3x minus 2y. So x, y, z is in L. L is the solution of this equation, the solution space of this equation. So x, y, z is x, y, and z has to be this, minus 5 plus 3x minus 2y. And again, I can decompose this vector. This is 0, 0, minus 5. That's just the number parts. Plus x, 0, 3x. Plus 0y minus 2y. Right? This vector is the sum of these three vectors. And this is the same as 0, 0, minus 5. Again, just as before, this is x times the vector 1, 0, 3. And this is y times the vector 0, 1, minus 2. So the solution space L is the set of all vectors 0, 0, minus 5, plus x times the vector 1, 0, 3, plus y times the vector 0, 1, minus 2, for any x and y in R, which is the same as the translation by the vector 0, 0, minus 5 of this set x 1, 0, 3 plus y 0, 1, minus 2 for x and y in R. And this is 0, 0, minus 5. And this is just the set W, the subspace W, which is the solution of the homogeneous equation. So here I have the solution space of the inhomogeneous equation. It's a translate of the subspace W by this vector. So this is exactly in the form of what we call an affine subspace.
I'm sorry, I have a question.
Yeah.
Can you just tell me the difference between so L is always used when it's inhomogeneous? Like, I don't know the difference between L and W. That's what I'm having trouble with.
Well, I mean, you can use any letters that you like, of course. All right, this is what you define. So I defined, in this case, I defined W to be the solution space of the homogeneous equation. W is the subspace of solutions of the homogeneous equation. That's how I define W. And I'm defining L to be the solution space of the inhomogeneous equation. Okay.
Okay, got it. Thank you.
And what we proved is that L is this particular vector plus W. So it's a translate of the subspace W by this vector. And that's what we define to be an affine subspace.
Thank you.
Okay. So this pretty much covers sections 1.1, 1.2, and 1.3 of chapter 1 in the text. And again, I'm going to go over all of this again in our next class. Monday is Labor Day, there's no lecture. So our next class is a week from today. And there's some homework due Wednesday evening, I think. But I'll set up a couple of review sessions between this Wednesday and next Wednesday when I'm on Zoom. And you can log on and ask questions about homework or anything else if you like. Okay.
Professor, the homework is just on Blackboard?
Yeah. Yeah, I mean, the homework on Blackboard, if you go to assignments, it's, certain problems in the text. That if you go to homework 1, it says, whatever the page number or whatever the section number is and which problems to do. So I think the first 2 assignments are posted.
And that for that we can like just upload like a scan of
For that, what you
our
have to
handwritten
do,
answer.
you write, you work out the solutions, write them out, scan your homework to get a single PDF document, and you upload that to Blackboard. And then I view it on Blackboard, and I grade it on Blackboard that way.
Okay, thank you, Professor.
Any other questions?
You said that we have to scan our homework and then upload it to Blackboard?
Yes. Yeah, it's exactly, everything is discussed in the information sheet that's posted on Blackboard about the
All
course.
right. Thank you.
Anything else? Any other questions? If not, enjoy the long weekend, and next class officially is a week from today. Bye all.
Thank you.
Bye.
Have a good day, Professor.
Thank you. You too.
Thank you, Professor.
One more thing.
Go ahead.
Can you switch to the page where you did the inhomogeneous equation?
This page.
I mean the one that ends with the right side having a 5.
Yeah. This is the equation. 5.
No, I mean the other page where you did the other equation. Yeah, that one.
Oh, okay, sure.
Thank you.
Okay. All right.
I have a question, Professor, about when the review sessions will be posted. You'll be posting them on Blackboard, right?
Yes.
Okay, thank you.
All right. Bye all.